Okay, so let us get started. So in the previous class, okay, looks like something happened with the recording. I either forgot to press start recording or something happened, and previous classes recording is lost. I'm not able to retrieve it. So sorry about that, but I'll try to make sure that. Are you able to see any indication in the top left corner that the class is being recorded? This meeting is being recorded.
Yes, sir.
Yes, sir.
Okay, fine. So hopefully the file is available this time, and I'll upload it as soon as it becomes ready. Okay, so let us get into the lecture itself. We stopped at this point in the last class. We were discussing about the properties of an unsaturated soil sample, and we discussed about 4 or 5 properties. First one, the porosity, which we define as the volume of voids by the total volume of the sample. And the range of values of porosity typically is between about 5% to 55%. Maybe in some extreme cases you might get 60%, but that's about it. The second property we looked at was the volumetric water content, which we denote by the letter theta, which is defined as the volume of water in the sample divided by the total volume of the sample. And because of the way we define it, this is how we have defined it. The value of theta can range anywhere between 0, a perfectly dry sample, okay, uh, to n, which is the porosity, for a perfectly saturated sample. Right? I told you that this can sometimes be a little bit misleading, because if you see a volumetric water content of 35% or 40%, our instinct is to say that the sample is 40% saturated, but that's not what this is. This particular value, the way we have defined it, it is only indicating, the value can only be between 0 and n, where n is the porosity of the material, which of course cannot be more than 55, depending on the type of soil, right? Okay. The third parameter that we defined was the saturation ratio, which is defined as the volume of water divided by the volume of voids in the sample, right? So now this value will always go between 0 and 1, 0 being a perfectly dry sample, and 1 when the sample is 100% saturated. Okay. I don't know why. Those of you who are trying to join the meeting, if you are not using the institute ID, it asks for permission to enter the room. So my suggestion is, please use the institute ID, your whatever your roll number at iattp.ac.in, that email ID to join, because otherwise I keep getting uh, this notification to let you into the room. If so, I don't know, but usually if you're using your institute ID, it just allows you into the room without any need for any permission and so on. Anyway, okay. So all right. So these were the 3 properties that we discussed. The fourth property is the dry bulk density. We denote that by the symbol rho B, is the mass of solids or the mass of soil divided by the total volume of the sample. Now this value B, I forgot to write it last time. Rho B typically ranges from around 1.6 to 1.7 or 1.8 maybe grams per cc. Um, that's right, right? The dry bulk density is typically around 1.7, 1.65, around that range. And then we define this other parameter called the particle density, which is the mass of soil or the mass of solids divided by the volume occupied by the solid. Now, okay, I have a question. Will rho m be less than or greater than rho b? With the definition, rho B, the dry bulk density, is the mass of solid divided by the total volume of the sample, and the particle density is the mass of solid by the volume of the soil alone. Now, obviously, the volume of the soil, the numerator is the same in both these cases. The denominator, in the one hand, we have for bulk density the total volume, and for the particle density, we have the volume occupied by the soil alone, right? So which obviously will be less than the total volume. So if the denominator is smaller, then my number is going to be large. So this typically uh, goes from around 2.6 to 2.75 or so grams per cc, right? So that's the kind of range of values that you typically expect for any kind of soil. Particle density is around 2.6 to 2.8 so, and the dry bulk density is about 1.6 to 1.8 grams per cc. Okay, so now I'll just quickly go through this example. We're not going to solve it. You can do this as an exercise for as a homework exercise. Okay, a soil sample was collected in the field with a volume of 75 centimeter cube, the total volume of the sample. The mass of the soil at the natural moisture content was found to be 150.7 grams, which means this is the mass of the soil including the mass of the water, including the mass of moisture, right? The soil sample was then saturated with water and found to weigh 153.67 grams. Okay, so natural moisture content, you have the weight, the mass, and then you saturate the sample and then find the weight again. You get the new mass, and then the sample was then oven dried and weighed, and the dry sample's weight was also, the mass was also measured. That's 126.34 grams, whatever. So you have these three uh, uh, masses, one at the natural moisture content, number two with completely saturated, and then number three when the sample is completely dry, oven dry. Okay, determine the porosity, volumetric water content under natural conditions, saturation ratio also at natural condition, bulk density, and particle density. Okay, so I will leave this as an exercise for you. So you know the saturated mass and the oven dried mass. So the difference between them will give you the mass of the water when the soil is completely saturated. You know the total volume of the sample. So that's known 75 centimeter cube. You also know the density of water. It's 1 gram per cc. So that's convenient. So then you do some simple mathematics. You will be able to figure out all of these different uh, parameters that you've been asked to find out. Soil porosity will be fairly obvious. Volumetric water content, again, fairly obvious. Once you get that, saturation ratio is going to be easy. Bulk density, you already know the mass, you know the volume of the sample. I mean, it's fairly obvious. Okay, so I will leave this exercise for you to solve. I think I already shared this problem in the PDF that I uploaded in the Google Classroom. So, okay, those of you who haven't yet joined the Google Classroom, please do so immediately. If you don't have the link for it, you can ask any of your classmates, or you can just send me an email and say, I want to join the classroom. Can you just, I think I've added pretty much everybody, but in case somebody is still left out, please quickly join the Google Classroom so that you have access to all that gets uploaded to the classroom. And then I also sent out a simple Google poll to schedule the midterm exam, and about 20 people have responded so far. Those of you who haven't responded, please respond quickly so that we can go ahead with with finalizing the date for the midterm exam. So far, 20 people have responded. I think the class strength is 31 or 32, something like that. So another 10 or 12 people are yet to respond. So please go ahead and respond to that, and then so which means please make sure you read your emails. Okay, the institute email ID, you're supposed to check it every single day, because I mean, not just for this course, other communication always comes to you through the email platform. So you're expected to not just look at your personal email ID, which is of course for your personal stuff, but anything connected to the institute will come to you through the institute email ID. So please make it a point to check that email at least once every day, so that you can keep track of what's going on. If any important announcement will typically come to you through email. Okay. All right. So moving on, I'm not going to solve this problem. I'm just going to leave this exercise fairly straightforward, and I'm sure all of you can do it. Okay. The next topic that we are going to discuss a little bit about is to find out the relationship between porosity and grain size. Okay. So what I'm going to do, I'm going to draw two conceptual pictures, and then I want you to tell me in which of these cases, uh, uh, how will the porosity be for these two different cases. Okay, so let us have, on the one hand, I'm going to take like a beaker or something and fill it with uh, soil particles of the same size. Okay, so now it's an idealization. Soil particles are not going to be perfect spheres, but let us say for the argument, I'm going to have perfect spheres of the same size in case A, and then I'll have a similar kind of a beaker, case B. Okay, so here let us say I have, now please also assume that all of these spheres that I'm drawing are all the same size. Obviously they're not, but let's assume they're all the same size. Let's say I draw a lot of these. Then on this side, I'm going to have slightly smaller spheres, but they're all again the same size, no difference. Okay, I'm only going to draw two layers. I'm not going to draw more than that. Okay, so let us say I have, in case A, slightly larger diameter, but they're all arranged neatly and they're all perfect spheres. They're arranged neatly one above the other. And then in case B, I have smaller grains, but again perfect spheres, all arranged neatly, in the exactly same manner. Now the question is, there's the porosity of uh, beaker A, Na, and the porosity of B. Now the question is Na greater than Nb, or Na less than Nb, or Na equal to Nb? So let's call this option 1, option 2, option 3. Okay, so how many people want to vote for option 1? Maybe you can raise your hand. Okay, I've got 4 votes for. You know what? There's a better way of doing this. This might be difficult. Okay, thank you, those of you who did raise your hands, but let's try this. Okay, which of these options is correct? Okay, so I'm assuming you're able to see the poll on your screens. Please vote for it. Please go ahead and vote on your screen. Na greater than Nb, Na less than Nb, Na equal to Nb. Okay, I'm not going to tell you how many votes. I mean, 7 votes have been received so far. How many people are there in the class? There's about 18, 19 people in the class, 16, 17 people in the class. More votes needed. Please go ahead, vote. 8 people have voted so far. Okay, I'm going to give you 10 seconds more. Just vote. Don't send chats. Just vote. 9 people have voted. There's another 10 people more who have to vote. Come on, quickly. I'm going to give 10 seconds. 10, 9, 8. Okay, I'm going to just end the poll. So 9 people have voted, and okay, 10 people have voted, and all 10 have voted for option A. I mean, the first one, NA greater than NB. If you can you can see the results. Now, unfortunately, all 10 of you are wrong. One person sent me a chat and said it's the second option, NA less than NB. So 11 people have voted. Well, unfortunately, all 11 are wrong. Okay, so let me just go back to the PPT. Now let us look at what the definition of porosity is. Okay, what is the definition of porosity? It is the volume of voids divided by the total volume. Okay, so let me do a simple exercise. Instead of calculating the volume of the entire sample, can I just take one box which has one sphere in it, okay, and find the porosity of this box? I can do that, right? Whatever is the percentage of pores in this box, it will be the same as the porosity of this entire sample, right? Because my spheres are all exactly identical and they're arranged in this beautiful, neat manner. No matter how I do it, I mean, if I just find the porosity of this one box, that should be the same as the porosity of this entire sample. Does everybody agree with that? Anybody disagrees with that? Just speak up. Okay, I don't think anybody disagrees with that. So let us say the side of this square is dA. Okay, dA. So then, what is the porosity Na? It will be volume of voids. What is the volume of voids? It is this portion, the shaded area that I'm drawing here. It is the volume of the cube minus the volume of the sphere, right? The volume of the cube is dA cubed minus volume of the sphere. What is the formula for volume of the sphere? It's 4 by 3 pi r cubed or pi d cubed, pi r cubed. So in this case, it will be dA by 2, right? So dA by 2 cubed. So that will be dA cubed by 8. So it will be, okay, it will be pi by 6 dA cubed. Everybody agrees? 4 by 3 pi dA by 2 cubed. So dA by 2 cubed becomes 8 in the denominator. So the 4 in the numerator cancels that out, and then you are left with 6. Okay, so that's the numerator of my the volume of voids divided by the total volume. What is the total volume? It's pi by 6 dA cubed. So what will you get? There is a dA cubed common in the numerator and a dA cubed common in the denominator. So I will get 1 minus pi by 6 divided by pi by 6, which is equal to something 6 minus pi by 6 divided by pi by 6. So 6 minus pi is about close to, if you just say approximate pi as 3, so it's half by 1/6, right? Oh, sorry, half. Oh, sorry, wait a second. 1 minus pi, 6 minus pi by 6. Did I do something wrong?
So the total volume, shouldn't it be dA cube?
Oh, exactly. Sorry. The numerator is dA cube, not pi by 6 dA cube. Sorry. Absolutely correct. Thank you. So the denominator is just the total volume. It's dA cube, not pi by 6 dA cube. Right. So 1 minus pi by 6. So that is 1. 2.86 by 6, something like that. So it will be around 0.45 or whatever it is. Close. So this will be okay. So now what I'm trying to say is, you see what happened when I solved for NA. The answer that I got was independent of DA. Now, if I do the same thing with another smaller cube with a smaller sphere inside it, I'll again find that the porosity here is independent of the diameter of the particle. Correct? So I'll get same answer. NB will also be 1 minus pi by 6. Right? So the porosity is actually independent of grain size if my particles are arranged in this beautiful manner. Okay, so the correct answer, if my particles are arranged, sorted like this and arranged beautifully, this is the correct answer. Na is equal to Nb. Okay, any questions on that? Any questions at all? Okay, so now we'll do a second thought experiment. Now I'm going again. I'll have two beakers, one on each side. Okay, I'm not going to spend a lot of time drawing this perfectly. I'm going to assume that you're understanding what I'm trying to say. Now here on side A, okay, I have side A and side B. In side A, I have the big particles are at the bottom, and the next size is above that, and then the even smaller size is above that. But they are arranged in this graded manner, right? All the biggest particles are at the bottom, the next bigger particle is above that, the next bigger particle is above that, and okay, so I'm not going to draw anything more. Okay, just 3 levels is enough to make you understand what I'm trying to say. Okay, so I have the biggest particles at the bottom, the next biggest particles above that, the next biggest particle above that, and so on. This is what you can call well graded. Well graded, right? There are grades of sizes and they're all well graded. Okay, I take the same particles that are here on in beaker A, I put them in beaker B, but what I do is okay, what I do is I put these smaller particles occupying smaller these areas. Okay, something like that. The total number of particles in A and B are exactly the same. Okay, it has the same number of large particles as here and here, but in the intergranular spaces, I fill in these smaller particles, which in the beaker A they were arranged one on top of the other. In beaker B, I just fill them in such a way that they just go and occupy the pores in between. So this is well graded. This is well mixed. Okay. In case B, soils are well mixed. The big particles and the small particles are all together. Okay. In case A, they are all graded and sorted. Right. The biggest particles at the bottom, next biggest above that, the next biggest above that, and so on. Now, I don't think I have to mention in this case what the relationship between Na and Nb will be. Is it either Na greater than Nb, or Na less than Nb, or Na equal to Nb? What do you think? Option 1, option 2, option 3. Which will have greater porosity? Okay, anybody would like to comment on this quickly? I don't want to do one more poll. Nobody? Oh, you want to do a poll? Okay. Oh, okay. Let's. Oh, which of these options is correct? Same thing. NA greater than NB. NA less than NB. NA equal to NB. Okay. Go ahead. Please vote. The poll is live. Five, 7 votes so far. 9, 10, 11. Good. Okay, we've got 11 votes so far. So I can let me just end the poll unless anybody wants to vote. Okay. See the results. 12 votes so far. 11 people voted for NA greater than NB, and that is the correct answer. The porosity of the well graded um, uh, beaker will obviously be greater than the porosity of the well mixed one. Why? Because when you are well mixed, the smaller particles are occupying the pore volume between the larger particles. So obviously what, oh no, okay, I won't say obviously. So what is happening is the pores, the larger pores between the larger particles, those volumes are getting occupied by the smaller particles, right? So therefore, there is less porosity left because that porosity which used to be vacant is now occupied by a smaller particle. So therefore, the porosity of the well-graded system will be much higher than the porosity of a well-mixed system. Right now, this is closer to reality, right? The previous slide, whatever I showed you, just was to illustrate the point that this porosity is actually a grain size. Now, this example that I have quoted to you, that a well-mixed system will have a lower porosity than a well-graded system, is also independent of grain sizes. These grain sizes can vary from anywhere to anywhere. It could be varying from 10 mm to 2 mm, or from 2 mm to 75 micron, or whichever range you take it. If you take it well graded versus well mixed, this this will be true. Na will always be greater than NB. Okay, so that's the correct answer. Okay, any questions before we move on? This is just, conceptual ideas. Of course, soil is not going to be perfect spheres. Of course, they're not going to be arranged, in this kind of, very rarely in nature you will see these kinds of arrangements. Usually, it's a mix of all kinds of grain sizes in one sample. All right, let's keep moving. There is also a connected idea, which is that of dual porosity. Now, you might not be familiar with this terminology. Now, imagine I have a rock. Okay, let's say I'm taking a sample of rock. I'm just breaking out a block of rock. Okay, and this rock has got some fractures in it. Okay, so these fractures, let's say they're just running across they're actually very thin. I'm going to exaggerate their thickness a little bit. Okay, so I have different kind of fractures running in different directions in this rock. Okay, so I just made some random number of fractures in this particular of rock. Okay, now this kind of a sample where a rock, but the rock is not compact and without fractures. It has some fractures running through it, some arbitrary number of fractures of arbitrary lengths, arbitrary thicknesses, and so on. Okay, so now what happens is, in this system, there are two kinds of porosity. One porosity is what is called the primary porosity. This primary porosity is also referred to as the matrix porosity. This is the pores. These rock particles are basically very, very fine, fine grained, and they are all, what is it basically? It is very old soil that has been compacted under a lot of pressure and has become very hard, right? But those particles will still also have some porosity in between them. So this is what is called the primary porosity or the matrix porosity. Okay. Then I have the secondary porosity, which is the fracture porosity. So when I say porosity, there is actually, the fracture is just vacant space. Okay, so there is the fracture is not going to have any porosity in it. It just has empty volume in it. The whole thing is an empty. Okay, but if you look at the whole sample, a fraction of the area of the sample is the fracture, right? So if you look at this, it's hardly 5% of the total area, or 2% of the total area is the fracture, right? Total volume is the volume of the fracture. So you have these two kinds of porosities in a fractured rock. One is the primary porosity, which is the porosity of the matrix, of the rock matrix, right? Which is the rock that comprises the block. And then the second type of porosity is called the secondary porosity, which is the volume of the voids created by the fracture itself. Okay, now fractured rocks behave very differently from a normal porous medium, right? Because in a normal porous medium, there is no secondary porosity. There's only one primary porosity. There's only one porosity, right? But in these systems, you have a dual porosity. Now imagine if this rock was fully saturated with water, and you take it out. Okay, what will happen? Immediately, instantaneously, all the water that is present in the fracture will immediately get drained out, right? Because that water is not held back very strongly, but still some water will be left in the primary porosity. Now the primary porosity is not going to be huge. It's going to be very small. It might be 2%, it might be 1%, 3%, something like that. But the initial whatever water drains out of this sample will all be the secondary porosity. And only then afterwards, water that is stored inside the rock, which is very small, very insignificant portion, only then it will be released. So that's the primary porosity. That's what's stored inside the rock. Okay. So these systems behave very differently. That's why we have this specific terminology for fractured rocks, which we call the dual porosity. Dual means double. Okay, two. Okay. Any questions before we move on?
So I have one question.
Go ahead.
What is the practical significance of this dual porosity? Does it contribute in landslides kind of calamities happening?
Okay. Now, landslides is a complicated topic. Okay. Um, I don't know if the secondary porosity plays a role in landslides per se. It might. I honestly am not an expert on landslides. What I can say is, when you say what is the practical significance. Now, if you look at what is that? The southern part of India, which is called the peninsular India, where you have the Deccan Plateau. Now, in the Deccan Plateau, most of the area, which is basically Maharashtra, Telangana, Andhra Pradesh, Karnataka, Tamil Nadu, except for regions where there are the big rivers, Krishna, Godavari, and Kaveri, the rest of the place you will find hard rock. And this hard rock, because it is Deccan Plateau was created millions and millions of years ago, that rock is also been fractured, right, over a period of time. due to various processes, including weather and human interference and all of that. The You have very old rock, and that rock is cracked. Now, what happens is these fractures, as I said, will also hold water in addition to the water that is held by the water held by the rock is very insignificant. So what happens is when you drill a well into a fractured rock, right? Now, just imagine this. Um, Suppose I have my house over here, okay, and my neighbor is living over here, okay. So my neighbor drills a well and hits this fracture, okay, at a depth of, let's say, 50 feet. My neighbor has drilled a well, and at 50 feet they've hit a fracture, and because the fracture has water in it, my neighbor has found water at 50 feet, okay. And depending on how well connected this fracture is, you may even get sufficient water for many months, right? Because every time there's rainfall, the rainfall fills the cracks, and so you may get, depending on how much water these people use, you may get significant amount of water, okay. Now let's assume that this fracture is not there, okay. Then your neighbor says, hey, you drill a well, man, you will get water at 50 feet. So you believe that, and you also drill a well, and then you keep drilling, nothing's coming, and then at 500 feet or 600 feet you hit water. It's the same fracture, okay. I mean, I'm showing it as if it's the same fracture. It could be another fracture also, but you see how much variability there will be between one user, one guy, and the next neighbor. Now maybe the distance between these two houses is only 100 feet, okay, but this person got water at 50 feet, this person got water at 600 feet, okay. So this is very highly uncertain. Nobody knows what, because the fracture is not visible to us from this at the land surface. When you're standing there, you can't see the fracture, it's invisible. Nobody knows where the fracture will be. So then if you are lucky, you will hit it at 50 feet and you may get enough water. If you are not so lucky, then you have to drill 600 feet, and then of course the cost of drilling 600 feet is very, 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 very high. The cost of drilling 50 feet is comparatively like 10 times more expensive, 10 times, right? So that's one of the practical significance, and therefore you will see people, who will say that, I will find out whether you will get hit water or not. Those guys come with a stick and they'll walk around, and then where the stick starts spinning, they say, drill the well here, you will hit water, and so on and so forth. Those guys are called water diviners. Have you heard that? I don't know if you've heard that phrase. Or some
Yes,
people,
sir, we have a.
they walk around with a coconut or something, or they walk around with one stick. They walk around, and then they'll suddenly the stick will start spinning. Okay, basically magic trick that guy is doing that you don't know. Okay, then you say, this is the spot, drill a well here, and then not only will you give that fellow some money, then you will have to go and drill your well, and there's no guarantee you will hit water, or whether it will hit up to 50 feet or 100 feet or 200 feet, whatever it is, right? So the practical significance is the uncertainty, because this whole thing, I've now drawn a cross section where I've made it visible, but in reality it's not visible. You just look at land surface, you don't know where the fracture is. So you will hear these stories of one neighbor saying, I hit water at such and such a depth, my neighbor hit water at much more deeper, and so on. The practical significance is the uncertainty that this causes, okay. And of course there are other implications. We'll talk about that a little bit later when we talk about the impact of pumping and so on, right? And this is the simple practical significance is the uncertainty in finding water, right? Because eventually we all need water to survive. So that's one practical significance, okay. Anything else before we move on? Okay, let's so I've just kept this slide from before just to quickly derive equation, but I'm going to assume everybody knows Bernoulli equation. Let's go ahead and come to Bernoulli equation. So Bernoulli P by rho g, plus v square by 2g plus z. That's our classic Bernoulli equation. Everybody is aware of this, even mechanical engineers, so no problem. So that the summation of these three terms is referred to as total head, right? We all know this. So P by rho g is the pressure head, also sometimes referred to as the static head. V square by 2g is the velocity head, also known as the what is it? Kinetic, not kinetic, dynamic head. And then Z is the elevation head or the datum head. So these three components together, when you add them up, you get what is called the total head. Now, when it comes to ground, this V square by 2g term is very, very small. Okay, V square by 2g, the velocity head or the dynamic head, is very small for groundwater because typically groundwater moves at the rate of, let's say, 5 meters per day, 10 meters per day, and so on, right? So 5 meters per day in meters per second will be what? Will be 5 divided by 86,400 meters per second. Be a very tiny number. So something 10 to the power minus 5 or something meters per second. Then you do v square by 2g. When you square 10 to the power minus 5, you'll get 10 to the power minus 10. Right? And then divided by 2g, and g is another 10. Right? So it's some 10 to the power minus whatever. Okay. So basically, this v square by 2g term is extremely small for groundwater because in surface water, water moves at the rate of 3 meters per second, 5 meters per second, and so on. Here it is moving much, much slower. Even if it moves 100 meters per day, it's nothing, right? So v square by 2g term is typically ignored in the Bernoulli equation when it comes to groundwater. Velocities are very small. Okay, so for all practical purposes, because v square by 2g is so insignificant, Bernoulli equation in groundwater, we just consider P by rho g plus Z. We just ignore V square by 2g. Okay, this P by rho g plus Z, the pressure head plus datum head or the elevation head, the summation of these two is referred to as the piezometric head or the potentiometric head. Both terms are used to refer to the total in groundwater. P by rho g, static head, a pressure head, plus elevation head Z is referred to, the summation of these two is referred to as the piezometric or potentiometric head. Okay, so this is something that you have to keep in mind in the context of groundwater as we move ahead. Okay, any questions before we move on? Okay, so now this pressure head, when it comes to groundwater, here again there is a distinction between the unsaturated zone and the saturated zone. Okay, so let me just draw quickly. I have the land surface and then I have the water table. Okay, so this is the water table over here. This region up to the water table is the unsaturated zone, and the region below the water table is the saturated zone, SAT. I'm just writing it short. Okay. Now, by definition, the water table, what is the pressure at the water table? What is the pressure at the water table?
Atmospheric pressure.
Atmospheric pressure. Why? Because the the zone above it is unsaturated, so the air is connected all the way to the atmosphere, right? So whatever the pressure in the atmosphere, the pressure at the water table will also be the same as atmospheric pressure. So here, let's say I'll call this point 1. So at point 1, we have P atmospheric pressure at point 1. Now I'm going to draw 2 points, one point above point 1 and another point below point 1. So let's say this height is h and this height is also h. Okay, so now let's take point number 3. What will the pressure at point number 3 be? Will it be greater than pressure at point 1 or less than the pressure at point 1?
Greater than
Okay, how much greater?
uh, rho GH.
Rho GH. Okay, so pressure at point 3 will be P atmosphere plus rho GH, because we are assuming that uh, hydrostatic pressure applies below the water table, and that is more or less accurate because, again, as I said, the water is moving so slowly that for all practical purposes you can think it's almost static. So therefore the pressure in the water below the water table is simply atmospheric pressure plus rho gh. Okay, now what about pressure at point number 2? Will it be the same as atmospheric pressure? Will it be less than atmospheric pressure or something else? Or it will be atmosphere minus rho gh? What do you think? Okay, how much?
Sir, it will be less than Newton 1 into.
It will be less than atmospheric pressure.
Yes.
Okay, that is correct. Okay, anybody thinks it will be the same as atmospheric pressure? Okay, so I'm running a little bit short on time, so I'll go towards the answer. So P2 will be less than atmospheric pressure. It won't be P atmosphere minus rho GH. We can't say that because it depends on so many other factors, but it will definitely less than atmospheric pressure. Now, this is a little bit of a slightly confusing idea. Okay, I'm going to try to explain this by taking two examples. Now, let us consider two samples of uh, soil. Okay, so I have, let's say, some soil particles. Again, I'm just drawing quickly. Okay, so now let us say I have, in this case, I have the complete void filled with water, saturated. Okay, and here in the first one, I only have a little bit of water occupying some portion of the, something like that. Okay, what happens is, if you go back to your fluid mechanics and think about what you have learned already, BTech, you will remember that there are, when it comes to surface tension, there are two types of forces. One is what is called the cohesive force, and the other is the adhesive force. The cohesion or the cohesive forces are forces between molecules of the same type. Okay, adhesive forces or adhesion is the force of attraction between molecules of different types. So that is usually referred to in the context of, let's say, glass and water, or steel plate and water, or whatever it is. Or you can imagine the lotus leaf and water, where the lotus leaf does not like to be in contact with water, or the water does not like to be in contact with the surface of the lotus leaf. Or if you think of a plate which has been oiled, if there's oil on that plate and you put a drop of water on it, the water will uh, will want to avoid being in contact with, will want to reduce the surface area that is in contact with the metal surface, because there is oil in between and oil and water mix, right? So it doesn't want to be in contact with. But in general, soil particles would like to be in contact with water molecules, right? So there is a strong attraction between the soil particles and the uh, water molecules. Okay. Now in this case, let's call this A and call this B. In case B, the soil is completely surrounded by water. So all its uh, surfaces are in contact with water, right? So there is no unbalanced force trying to attract more water, because the entire surface is in contact with water, so it cannot handle any more water. It doesn't need any more water. But in case A, some of the surfaces are in contact with water, and the remaining surfaces, which are dry, would like to be in contact with water. So they are applying kind of they're trying to pull water towards themselves. It's like a suction. Okay. And whenever you have suction, okay, it is, see, what is happening is here at the microscopic level, there is uh, the soil particles want to be in contact with the soil water molecules because of the attraction between the soil particles and the water molecules. So that microscopic effect of uh, uh, desire to be in contact with these water molecules results at the macro scale, it results in a kind of a suction. Okay. It's called the pressure head in an unsaturated sample is also sometimes referred to as a suction head. Okay. And suction indicates vacuum and so on. Whenever you have vacuum, it must be less than atmospheric pressure. So that is why the pressure head, I'll stop with this, pressure head in an unsaturated soil sample is below the atmosphere. Okay, just keep this in mind. So whenever you have a saturated soil sample, you will call pressure, I mean, you will call it pressure because it will be greater than atmospheric pressure. Whenever you have an unsaturated soil sample, have the suction, uh, basically particles wanting to be in contact with water. So they are trying to attract more water molecules toward themselves. So that results in a suction, and suction by definition is something that's below atmospheric pressure. So in an unsaturated soil sample, you have suction head, which is the same as pressure head, but we just call it suction head to denote that it is below atmospheric pressure. Okay, I'll stop with that for now, and we will meet again on, I think, Tuesday. All right. I might add some reading material or something over the weekend, so you can take a look at that also. Okay. All right. Take care, everybody, and we will meet next week. All right. Bye bye.